and a lot of things we could not do or we could not think. Now, thing is,
Okay.
fingertips. To spend time.
So we can start now, sir. Yes. A very good evening. A very good evening to all of you. Today we have the third presentation, actually second progress of Rupjuti. And with us, the members are Dr. Bhavesh sir from Agriculture University. He is a scientist there. Dr. Pushpendra sir from Central University of Jharkhand. And Dr. Rubul sir is also about to join. He is professor from BSSRB Golaghat. So with all the members' permissions, Rupjuti can start the presentation. He can start, right?
Yes, sir.
Okay. Good. Thank you, sir.
So, good evening, respected panel members and respected teachers from Kazina University and dear students and my co-scholars. So, I am Rujyoti Sutia, currently pursuing PhD uh, under the guidance of Dr. Deficiency sir. And my research topic is AI-driven framework for real-time uh, monitoring of nutrient deficiency in rice using leaf image analysis. And this is the presentation for my after completion of my fourth semester. So actually the problem, I'm working in the field of agriculture and from last 15 years and working in Assam Agriculture University. So I am facing some problems like we have less experts than the problems. Actually, when we visit to field, we have lots of problems like how to solve this problem or how to what is the solution for the problems like rice for different vegetables or different crops. So the main problem is to uh, provide support to the farmers or annadatas in their farming activities. So my problem statement is there is a significant gap in developing a robust. The main problem is the ground problem was is the farmer has less expertise, so they have to do their work with their lesser knowledge. So if we have something, we IT people have something to give to them so that they will be able to uh, monitor their field with the help of the devices or you can say different applications. So we're planning to develop a model, develop an AI-based framework which will support the another in finding solutions for their problems. So my case is for the major crop for India, that is the rice. So for rice, uh, uh, we're developing a framework where they will be supported by providing nutrition. If they have some nutrient deficiency symptoms in their rice plants, then they will be able to identify with the help of the app or you can say the application or the web application. So with the help of that, they will be able to identify whether it is nutrient deficient or there is the rice plant is healthy. So we have three objectives. The first objective is to perform a comparative study of image denoising and enhancement techniques, and hence to design and implement an adaptive image preprocessing and enhancement pipeline suitable for pre-processing rice leaf images captured under field conditions. So first objective was taken because uh, the farmers first the problem is we have to collect we have to take sample from the real field. So in field conditions there will not be sufficient light, may not be sufficient lighting, or you may not have that kind of devices which can capture sharp images. So we may face different problems. The main problem is that we have to classify uh, the rice plant whether it is efficient or healthy. But the basic problem is there is whether the image is taken with in sufficient lighting condition or with enough or capable imaging devices. So the basic problem is the pre-processing. So we have to pre-process those images collected from field. So therefore we have taken the first objective to design a pre-processing pipeline first, so that we have a clear image for classification. So then second objective is to evaluate and fine-tune deep learning models for accurate classification and prediction of rice nutrient levels. And I'm taking NPK, nitrogen, phosphorus, and potassium because these are called major nutrients for any plant. So these three compounds are required for growing any kind of plant. So we are taking NPK and nitrogen, phosphorus, and potassium. And after that, the third objective is to develop a lightweight and user accessible prototype, which will be available with the farmers. So they will have so we are planning to, or we are designing the model taking into consideration the lightweight model, because the farmers may not have a hi-fi or high configured mobile devices or edge devices. So they have some most of the farmers have the smartphones, but they have the lower uh, you can say lower configuration. So we are designing a model which will be lightweight. So and that model will be application will be available made available for the farmers. So these are the three objectives. So we have already completed the first objectives, which I have presented in the last seminar. Though we are still I'm presenting few of them, so that the continuity, because the continuity is there. What I'm currently working is definitely depending on my past works. So I'm going through the previous works. So first, I have done critical review on rice nutrient monitoring using AI-based techniques. So what are the techniques available and how they are performing? I have already reviewed those things and already presented in an interesting seminar, and it's already published in a book as a book chapter. Then I have done comparative study of image denoising and enhancement techniques for processing digital images of rice leaves. So this is the first part of the first objective. So here we have compared the commonly available filters. So this is not about deep learning or deep learning models. This is on the basic filters are Gaussian filter or different filters are there, common filters are there. So those are compared, and their performance was uh, evaluated combined with clay. So the contrast limited adaptive histogram equation was applied after applying the filter. Then thus I'm directly going to the results section because it has been done in the second semester. So just I'm for continuity I'm just presenting this. So this is already the work already presented in international conference organized by Kaziranga University, and got this paper award and published the abstract in Data Driven AI, and also the paper has been published in International Journal of Agriculture and Natural Sciences on September 2025. So the final findings are there. So when bilateral and BMTD denoising combined with clay with 0.5 uh, intensity and 5 by 5 tile size. So we have better result for removing Gaussian noise. and soluble noise is best removed using median filter with Clahe 0.5, 5 by 5. So here 0.5 is the intensity and 5 by 5 is the tile size. And uh, here we have found that BM3D reduces the percentage speckle to the lowest degree, and the bilateral filter more effectively preserve the fine edges depending on one's priority for noise separation or edge detail. So because we actually want both, we need the edge detection or also a noise separation. So sometimes here we have actually uh, I already have presented that when we apply BM3D filter, we get clearer image, but some of the details vanishes when we apply BM3D filter. So the main problem with this study we faced that they are using this actually we are uh, putting the same filter for different types of noises. So ultimately, this is the case. Actually, I have for a while reviewing, I have seen that most of the studies have been done like that. That they will pre-process the image with any of the filters. Basically, the Gaussian filters are used commonly. Gaussian filter is used, and then after those images are used for classification. So it is like something like it is called blanket dose. If we some image doesn't require pre-processing, that there we are also applying same amount of same intensity of the filter if required, then also applying, or if there is no Gaussian noise, there is a salt noise, there also we are applying Gaussian noise. So that is the main problem in my first study where we have compared the traditional filters. So therefore we have tried to design and implement an adaptive music processing and enhancement pipeline suitable for pre-processing live images uh, captured under field conditions. So why we are mentioning under field conditions? Because as I have already mentioned that when we capture the images from field condition, we may have different types of noise. We cannot say that we will get a Gaussian noise or random noise or speckle noise. We may have different types of noise. We may even a little bit of salt noise may be there. So different types of noise we will get due to the lighting source, due to the environmental conditions like due to cloud over day we are getting lesser light, or maybe due to the lens artifacts, because the users or you can say the farmers will use lower configuration mobiles. Their lens or their imaging device may have some errors, so they can produce noisy images. So we have designed a deep learning based uh, architecture for pre-processing image, and we named it as need, because as it is the need before processing any image, so we named it as need, because need meanings the name of the meaning of the need is noise estimator and expert denoiser. So there will be two components in the need architecture. The first one will be the noise estimator model. That means we have two models, as you can see in the diagram. There will be two models. One is the noise estimator model, and another is the expert denoiser model. So this is a simple classification model, noise estimator model. So it will estimate the type of noise and level of noise. So is a classification model which will find out whether there is a noise, and if there is a noise, if what type of noise is there, and what is the intensity of the noise. So then the noisy image, the noise type and noise level will be supplied to the expert denoiser model, or you can say denoiser, which will denoise based on the condition. What what is the type of noise and what is the level of noise. Based on that factor, the denoiser will denoise the image, and after that it will produce a clean image ready for processing or further classification. So actually we have presented this in last semester. So as I'm in saying, so this is the uh, these are the layers of the need noise estimator model. And the performance of the noise estimator model here we can say in noise type prediction, its precision is 94.9476, recall is 947, and F1 is 9469.9469. And while predicting noise level, its precision 0.9907, recall 0.9906, F1 score is 0.9906. And here you can see here that in the confusion matrix, so it is predicting 1500 images. So here the expert denoiser model, we have developed two variants. One is the light models with lesser number of layers, and second one is the deep model. So the needline model has 46 layers, and this is the structure. And both, in case of both the models, we have used the film layer, feature-wise linear modulation layer, which adapts filters based on noise metadata. That is that I already have mentioned. Based on the noise metadata, it will denoise the image. Then another model is the deep model. So let us check the performance of noise estimator. We have used total 5000 images for denoising. So we have observed that PSNR increase in 3192 samples, that is 63.84 percentage images, and decrease in 1807 images, and SRM increase in 4420, 88.4% images, and decrease in 5.38 images, and 3,311 samples, it remained the same. So average increase in SSM is 42.5, and time required for denoising 5,000 samples is 79 seconds. So as I have already mentioned that we are designing a lightweight model, and both noise estimator and need light model is a lightweight model. I will discuss it in later experiment. So this is the visualization of the prediction of noise estimator plus expert model denoiser light, that is in short form need light model. And this is the deep model. So here we have 120 layers. So this is the structure of the need model, need deep model. So here we have seen that PSNR increase in 3,556 samples, that is increase in 71.12% images, and decrease in 1444, that is 28.88%, and SSM increase in 4,645 samples, and 92.90% increased, and decrease in only 354 images, that is 7.08 images. And the time required for denoising 5,000 image samples, it takes 99 seconds only. So this is the visualization of deep model. So the observation from the two lighter denoiser and deeper denoiser model. So lighter one is a lower complexity and faster training. So achieve moderate PSNR 64% improvement, and SSIM 88% improvement. And here deeper is the higher complexity and slower training. So achieve stronger SSIM 93%, more about 93% images improved in SSIM, and higher PSNR 71%. So here better generalization to diverse noise types and levels, and once model is trained, it can process an image almost at the same time with the lighter model, that is around 4 millisecond higher than the deeper model, lighter model. So next, what I have worked in the last semester. So this is the comparative study of deep learning. So we have compared total 5 models: need light, need deep, then FFT net, DRU net, and noise to noise. And uh, so here, as I have mentioned, that we have developed 2 models. One is need light and need deep, and compared with the already established models like FFD net, DRU net, noise to noise. So
A few terms may be new to you, but try to note down those stuff. Okay, this is for the students, like PSNR or these things. See, sometimes of this kind of research presentations may be like, I am not going to use that term. But the thing is that the more patiently you listen and note down the things will help you in the near. So I request that all of you please seriously note down those stuff. Which is, yeah.
I hope the current slide you can see comparative study of deep learning based denoising techniques. Who is it?
Okay. So the first architecture to compare is the FFD-net, fast and flexible denoising network. It is a we can say one of the lightest denoising network. So this require the scalar map to that is the noise level map is to be provided to the model, so, and then it will denoise the image. And again, one of the heaviest model, UNet based dilated residual UNet model, the DRUNet is called. So here also we have to provide the noise level to the noise level to the model, and it will uh, uh, denoise the middle, denoise the image using the encoder decoder design. And also, as we have used in our need model, residual learning is here also implemented. And the last one is the noise to noise model. So this case is applied when there is no clean or there is no truth image image, uh, or we have only the noisy image. In that case, if we want to denoise the image, then we apply noise to noise model. So for training this model, we need 2 pairs of noisy image, and it is also effective in cases where there is no original or noiseless clean image. So we have used 1500 images level in nutrient deficient rice leaf images. So and here noise synthesized in case of FFT-net, we have used a noise synthesized dataset of Gaussian noise, and for other models we have used Gaussian, salt and pepper, and speckle and random. 4 types of noise are applied and of different intensity. In FFT-net also we have used Gaussian noise with different intensity, because FFT-net is specifically designed for Gaussian noise. Therefore, we have used Gaussian noise synthesized dataset for training. So this is the technical details while about the models. So FFT-net, we have used batch size 8 and epoch 20, and DRU-net 820, noise-net 820, noise estimator, expert denoiser, and expert deep and light. In these cases, we have increased the batch size as we have already evaluated the models, and uh, we have observed that they are better performing if we train with a higher batch size with higher number of epochs. So therefore, we are using a higher batch size and higher epochs in case of the need light and need deep model. And for other cases, we are using 8 by 20 because of that the case that we are using only CPU based message. No GPU is in while training, because while implementing, we are going to implement in a lightweight or you can say low configuration device. If we are test or develop it in a GPU based machine, so they will not work at last. So we are therefore using a lesser number of batch size and epochs for for training, because one of the reason that DRU net is very heavy. So if we increase the batch size or the number of people, it will take longer time or may not be trained with the normal machines. So therefore we are taking these things, and you can see there are parameters like we have FFT net with 8,54,000 parameters, and dear net with 5 crore 35 lakh 47,203 parameters. So it's the heaviest model. And noise to noise estimator and expert denoiser, these are like lightweight models, so lighter than the FFD net model. So here is when we have predicted with the test data, we have seen that F50 net takes 7 minutes, 37. Sorry, this is for training actually. So for training, F50 net takes 7 minutes 37 seconds. DR net takes 2 hours 31 minutes 1 second with the previous configuration. Noise to noise 11 minutes 6 seconds, and need light total 56 minutes 16 seconds, and need deep model 1 hour 39 minutes 29 seconds, and increase in
Excuse me,
PSR.
Rosary. Excuse me, Rosary.
Yes.
Yeah, that work done till now from that slide, it is not moving at my part. Whether it is happening only in case of me or in case of other online participants also.
Okay. Might be there might be some.
Maybe in case of me
Yeah,
only. In case of other participants, it's a work.
yeah. I'm restarting my presentation from the last visible slides.
Stop share. Means work done till now from that slide in case from here in my part it is not moving. It's stuck there.
Okay.
Yeah,
Work
maybe
done
because of
until
the internet problem. You just stop share and again reshare.
aku share করো না એટલે জুমল দাও share
Network like this.
network yeah
Actually, in KU, the current internet connectivity is very poor now. So maybe this is the reason. Can you see the slide?
yes sir yes sir.
Yes, sir.
Here also, yeah, Assam Agricultural University also the same case. Internet these days it's not working properly.
Okay.
Sir, is it visible now, sir?
Yes, now it is visual.
It is visible, sir. Is it going?
Okay. Fourth experiment. So these are the technical details of the models. Here I have listed in the table, and this is the training data where I have trained the models with 1500 images, with taking 80-20% training and validation testing data. So here we have seen that FFD10 model takes 7 minutes 37 seconds time for training. Dearonet 2 hours 31 minutes 1 second. Noise to noise 11 minutes 6 seconds. Need light model 56 minutes 16 seconds, and need deep model 1 hour 39 minutes 29 seconds. So here, if when we have tested with the test data, 300 numbers of test data, where test samples, we have seen that there is an increase of 100% images in PSNR and SSM with the help of the DRNet model. And the second performing is the need light model, where 74.33% increase in PSNR and 84% increase in SSIM. And need deep model, in case of need deep model, 68.33% increase in PSNR and 87% increase in SSIM. So these are the average PSNR and SSIM for noisy versus clean and denoise versus clean. So here we have observed that specifically the SMA increase with the help of need is much higher. And if we compare with, in the we will show comparison in next slides, where we will show you how they are performing with in comparison with the DRNet model. So this is the training loss curves. For first one is for FFD net second is for the dual unit model. Then this is the noise to noise model, and this is the second one is noise estimator model. The training loss graphs for need light model and need deep model. So this is the denoise model from each denoise images from each model. So first one is with first two images with FFD net model. So these are the images denoise with DRNet model, the noise to noise model, need light model, and need deep model. So this is the results. These are results with 15,000 noise synthesized newly noise synthesized data, where we have predicted 15,000 noise synthesized data. So here we have seen that the FFD net model takes 14.9 milliseconds to denoise a single image. DRNet takes 34.22 milliseconds. Again, noise to noise takes 10.57 milliseconds. Need light 17.52 and need deep model 19.44 milliseconds per image. And increase in PSNR. So we have seen that again the best performing three models DRNet, need light, and need deep. So increase in PSNR in case of DRNet it is 91.67, need light 65.40, need deep 60, and increase in SSIM 88.93 in case of DRNet, and 84.13 need light and need deep 82.93. And here also we have seen the picture here that the average improvement in the PSNR is almost same in three models, but increase in the SSIM is higher in case of need light model and a need deep model. So which reflects that the uh, structural improvement is there in with the help of the need light model, need light and need deep model. So here you can see that. Hello. Hello.
Rosity,
Oh yes. Hi, Bhajakob.
ঐ মানে হেৰিটো শ্লাইড খিনি কিন্তু মোৰ ক্ষেত্ৰত আকৌ যোৱা নাই এই বাকী কেইজনক সুধি চোৱাচোন বাৰু কি হৈছে প্ৰব্লেমটো না মোৰ ইয়াতে হৈছে নেকি মই জানিব বিচাৰিছো
আকৌ লাগি ধৰিছে হয় হয়
তাৰমানে অকল মোৰ ইয়াতে হৈছে নে বাকী পুষ্পেন্দু ছাৰ whether পুষ্পেন্দু ছাৰ in case of Pushpendu sir what or Abir Banerjee na so in case of them also it's happening or only in case of me it is happening that slides are not moving.
No, no, it
Can
is
you please
for all
confirm?
actually.
So it's for all
Okay,
actually
okay.
I'm
So
sharing
you
it
do one
again.
thing, sir. Sharing not required.
No,
That slide,
screen share karo.
sharing means
Screen share.
that
Okay, slides without slides showing.
slides or without slideshow mode, you will have to pass it in one by one. Then it will work. Yes,
Okay.
now it is the graph we are seeing.
Okay.
Slideshow not required. You just click on it.
Okay. So here we have given the results from the 1500 noisy images which are predicted with the different models, different type models. So here we have seen that noise to noise model is performing faster, but the performance is very poor. But the top performing models are FFD net, sorry, DRNet, need light, and deep model, where we have seen 91.16% improvement in PSNR and 88.93% improvement in SSIM in case of DRNet, and 65.4 and 84.13 in case of need light, and 60 and 82.93% improvement in case of need deep. So this is here we are presenting in it graphically the average PSNR.
Eco where set sound to one of the
ভয়েস আপনার মাইক অন হয়েছে নাকি
নহয় আমাৰ on হৈ আছে
মোৰটো অফ হৈ আছে, একো নাই, মোৰটো অফ হৈ আছে।
Oh, no, what I is.
এইটো on হৈ আছে বাৰু মোবাইলতো on হৈ আছে
নাই।
কেৰি অন কোনোবাৰ on হৈ আছে
So,
কিন্তু আমাৰ ইয়াত ইকো হোৱা নাই মাতটো, আমাৰ ইয়াত আমি ঠিকেই শুনি আছো।
okay, sir. Then okay, no problem, sir. Uh, so this is the average PSNR comparison across different models. So here we have seen that the need light and dearonate and need deep, three models are performing very well. And in case of SSIM, as I have already shown in the data, so need light and need deep model performed better. Then here, this is the box plot where we have seen that the in case of need light and need deep model, so they tries to improve the PSNR to a specific confined range, and maybe some outliers are there in the higher range but not in the lower range, which we have seen in case of noise to noise model. Then again, this is the violin plot of patient distribution, where again we have seen that here in case of dearonate, it is distributed from around 10 to 60, and but in case of need light and need deep, it is confined to a range within 25 or to around 50. So this so then this is again a box plot where this is SSIM. So we have observed from the data that in case of DRUNet, some images are there which are deteriorated extremely, like their PSNR is around 12 to 13, which the unit cannot improve to a good range. So we have seen that with the images with lower PSNR like 12 to 13, it just improve only one or two, that is 14 or 15. But with the help of need light and need deep model, we have observed that the 14 or 12, the images with PSNR or SSM with around 0.12 was improved to a higher range like a zero point 0.8 or zero point 0.9, and again PSNR like 12 13 to 30 or 40. So this is a good actually result from this need light and need deep model. So here again in violin plot where you can see clearly that it is confined to a specific range between 0.8 to 1.0 in case of need light and need deep, and in case of DRUNet it is distributed from around 0.12 to 1 point something, sorry 1, around near about 1, near about 1. So these are the key findings from the study. The noise to noise and FFT net are faster and lighter than the other three models. Regarding training and processing an image, however, they are the least performer among the five. Then DRUNet performs other models in denoising image. With test data of 300 numbers, we have seen that PSNR and SRM increase in all the sample images, and PSNR increase in 91.67 of samples, and SSIM increase in 88.93 of percentage of samples from 1500 noise synthesized data. Both the need models perform well, where there is 74.33 and 68.33% increase in PSNR, and 84% and 87% increase in SSIM with test data, and 65.4 and 60% increase in PSNR, and 84.313 and 82.93 increase in SSIM with 1500 noise synthesized data by light and deep model respectively. So as we have seen from the raw data, as I have already mentioned that PSNR and SM denoise images ranges from 14.45 to 56.03 and 1.123 to 0.998 for DRUNet model. So here the range is big, big range, that is from 14.45 to 56.03 dB, and again in case of SIM 0.123 to 0.998, where the noisy image has the range from 13.87 to 63.35 dB, and SSIM 0.1228 to 0.9998 So here you can say the lowest image, the low actually most deteriorated image has the PSNR 13.87, which is improved to 14.45 by DRUNet, but it was improved to 29.26 by the need light model and 27.99 by the need deep model. And again, if we can observe the SSIM, so the noisy image has the highly deteriorated noisy image has the SSIM 0.1228, and which was improved to 0.123 by DRUNet model, and but in case of need light and need deep model, it was improved to 0.809 and 0.793 to 792. So from the above data and the box plot and the Biden plot for PSNR and SSIM distribution, so need models enhance or resource the most deteriorated image to great extent by improving PSNR about 27.99 and SSIM above 0.79, but DRUNet was unable to handle the worst case. So among the three top performing models, DRUNet, then need light and need deep model. So we have already observed from the experiment that DRUNet is the heaviest model with the highest trainable parameter around 5 crore 35 lakhs 16 4833 parameters, and highest size of the train model 614 MB, which will not be used for implementing into lightweight edge devices. And the need deep model is a very light model as compared to the DRUNet model. It has only 8 lakhs 73,527 trainable parameters, and the train model size is 10.4 MB only. And the neat light model is the lightest among the three. It has only 2 lakhs 21,045 trainable parameters, and the model size is only 2.76 MB. So which can be deployed to any kind of you can say lightweight edge devices. And for if we study the time required by the best performing models, so DRUNet requires around 168% more time, for as I have already tabulated in the previous slides. So 168% more time for training the model and 95% more time to denoise a single image. And in case of as if you compare with need light model, and requires 52% more time for training the model and 76% more time to process the image as compared to the need deep model. So from the whole study, we can conclude that the proposed lightweight need light model achieves the practical balance between reduced parameter weight and strong performance, ensuring efficiency without sacrificing perceptual quality. So due to its lightweight nature, it is suitable to be implemented in edge devices. So this is the findings. These are the findings from the comparative study between the deep learning based models for denoising images. And we have after that we have started prepared a research paper with the findings from the study, and will be submitted to a journal within July 2026. Then next event is on. So my next experiment was is to evaluate and fine-tuning deep learning models for accurate classification and prediction of rice nutrient levels using annotated rice leaf images. So taking into consideration my with the my past development of the need model, we're using another component to classify NPK levels in rice plains. So here we have designed a pipeline, so and named it as need rice leaf net. So need means noise estimator and expert denoiser, and rice crop evaluation. And as we are using leaf imaging, so we are using leaf, and it is a network deep learning network. So we are naming it as need rice leaf net. So it's a three-stage pipeline. The first one is the noise estimator, which predicts the noise type and noise level. Then the expert denoiser enhances the leaf image using the metadata conditioning, that is the noise type and noise level. And the classifier detects 9pk deficiency or the healthy class. So this three-stage pipeline we are actually working on. It's not completed. We are working on. We have to do more things, but still I'm presenting the current progress or what I'm doing right now. So this is the complete pipeline. So where the noisy Rice-Leaf images will be provided to the noise estimator, and again the noise level and type, and the noise in the image will be supplied to the film condition expert denoiser, which will give us given enhanced image as an output, and that image will be provided to the classifier network, and that will classify the four classes: nutrient deficient, potassium, phosphorus, or healthy. So this is the complete model of need rice leaf net. So we are actually planning to one one more component in the classifier network. One film model will be there, so which will take the noise level and other components from the noise estimator or the need model, so that it can uh, actually uh, it can do more the classification more accurately. So we'll trying to implement those things also. So this is the structure of the full complete rice leaf net model. So then input is the noisy I have written denoise image. Oh, sorry, it's okay, denoise image. So this is a rice leaf net. This is not a need rice leaf net. This is the rice leaf net model where only the denoise image will be provided to the rice leaf net model, where three residual blocks will be there, and in between we'll provide the noise metadata for Fisher modulation. The film conditioning will be there. Then global pooling, and after that fully connected layers will be there, which will classify the nutrient and the flow classes. So uh, this is our proposed model, and we're working on that. So actually here the classifier or the whole pipeline is a hybrid pipeline where we will use two components, the noise estimator and the expert denoiser as a Keras model, and the you can say the classifier will be a ResNet film based PyTorch model will be used, and one Keras PyTorch wrapper will be used to bridge between these two uh, architectures. So one we have Keras model and another is PyTorch model. We will use Keras PyTorch wrapper for bridging this two model, and this is the complete model where the noisy image will be there. Then noise estimation denoising, for noise estimation and denoising we will use Keras model, and there will be a wrapper to bridge between the Keras and the PyTorch model, and the PyTorch model will classify the four outputs. So we have implemented this, and we have tested few of the images. So this is I am presenting here for visualization. So the first one is predicted by the need rice leaf net light model, and second one is the need rice leaf net deep model. So here we can see that the uh, first one is a noisy image, and second one is a denoised image, and finally we have seen a denoised image, which where the classifier predicts it as a nitrogen deficient leaf image. Again, the same image is supplied to the need rice leaf net deep model, and here also it classified as a nutrient deficient rice leaf image. So this is the performance of the need rice leaf net light model with 1200 samples. So here we have seen that uh, the precision recall and F1 score and support. So for the four classes, so for healthy, we have 1.0 for precision, 1.0 recall, and 1.0 F1 score, and K deficiency, the precision 0.85, recall 0.73, and F1 score 0.79, and for nitrogen it's 0.97, 0.96 recall, and 0.96 F1 score. And for P deficiency, it is 0.75 precision, 0.87 recall, and 0.81 F1 score. And this is the confusion matrix. And so this is the ROC curve for each class. And this is the final results for this need Rush-Lipnet light model. So this is the visualization. So should I zoom the image to get the levels, or you can see like this, sir? Sir, am I
It's
audible?
okay. It's okay. Yeah, you're audible. It's okay. I think so. You can imagine from here. You can. No problem.
Yeah, if I can try if it is possible to zoom it. So is it visible, sir? So the first one is a true image with a class K deficiency. So second one is the noisy image, noise synthesized image, and the predicted image with the predicted class, the final image. So K deficiency. This is the second image. For 4 classes, where I have shown 4 images here. Then about this is the need rise sleep net deep model. So here we have also here we have seen that. So in case of healthy, the prediction is very accurate. Then as a whole, accuracy of the model is 88.17, whereas the accuracy of the need rise sleep net light model is 88.92. And here again we have seen that in 2 classes, healthy and nitrogen deficient, it is predicting its accuracy is very good. So this is the RC curve for each class, and these are the results. So improvement in case of PSNR, SSIM, and also classification accuracy, and you can say noise level and noise type accuracy is very good. And also the macro AUC is very good in case of both the models. Both the model has a macro AUC of 0.98. So this is the preview from the need deep model. So again, prediction from this is this is the side-by-side comparison of the two models. So this is need light model. The first one is the noisy image. Second one is the need denoised by Rice-Lipnet light model, and second one is deep model. So both the model is predicting accurately in case of this sample, and for the second sample also. So we have seen that in while working with these models, we have observed that a few in few cases are there where the model is not performing very well. For example, in case of potassium deficiency and phosphorus deficiency, we have seen lower accuracy. But in case of healthy and deficiency, it has showed a higher accuracy, like 100% in case of healthy and 95.67 to 97.30 in case of nitrogen deficiency. But for that, actually, we have a data set of a smaller size, which is publicly available in Kaggle. So we are using a data set containing only 1500 images. So we are planning to create our own nutrient deficient rice leaf image data set with the local rice variety Masuri. So for improving or we'll uh, try to provide more data for training these models to increase the accuracy. So we have already planned for this experiment. So, and second one that we have noticed that the model has a moderate accuracy like 0.89% around. First one is, and light model has 88.92% accuracy, and second one is 88.13. So around 89% of accuracy is there, but have a high AUC uh, of the both model, that is 0.98. That means the model have strong discriminative power, and with better calibration and ensemble method we'll try to push accuracy closer to the AUC performance, which is the target of our in our future uh, time. So we'll try to increase its accuracy to the high AUC level around sorry, around 0.98. So uh, and we have started the next experiment, that is rice nutrient deficient dataset creation. So we'll create a level image dataset of rice leaf images for nutrient deficiency detection. We don't have for Assam or for India, we do not have any rice leaf nutrient deficient detection data, sorry, deficiency image dataset. So we're therefore we are planning to create a dataset around. We are planning to create 5,000, but from 1,000 to 5,000 we will try to create. So for that we are we are using the rice variety Masuri, which is very popular in Assam. So we are already in the sowing phase, and so we are cultivating the uh, Masuri rice in disposable tubs of 20 per category. That is for we have four classes. So healthy and deficient, NPK deficient. So total 4 class. For each class, we use 20 disposable tubs. And the soil type, we have collected the nutrient exhausted soil.
Please conclude your presentation in short.
Sir,
Conclude your presentation.
okay, sir. Okay, sir. Sir, we have one or two slides more. So, okay, sir. So we have for this experiment, we have already collected the nutrient exhausted soil, and seeds of local rice variety Masuri are sown in nursery bed. So last sowing date is 21st June, and already collected the small plastic tubs for planting the seedlings. So uh, the works to be performed in the next semester will create a nutrient efficient rice leaf image dataset, and to improve classification accuracy with of need rice leaf net model will work to improve this accuracy. And finally, to develop a lightweight and user accessible prototype system for real-time rice nutrient monitoring and fertilizer recommendation using AI models. So uh, these are the slides we have, and if we have any questions and suggestions regarding my experiment on my research, kindly, sir. Uh,
Yes, now the respected members, sorry that we have taken more time than the 4:30 actually we have to conclude, but because of the network problems that occurs in between, so this time exceeded. So I now request the respected members, if you have any suggestion or questions you have, then you can please put forward.
Uh, Thank you, Rupjiti, for your nice presentation. Am I audible, Rupjiti?
yes, sir.
Am I audible? Okay, okay.
Yes, sir. Yes,
You
sir.
have presented. You have presented very nicely, and the slides are also very good. I think so, and I think so. This work is going on in the right direction, and that is what from my part. And if any problem will be there, I'm here only. We can meet physically. Okay.
Yes, yes, sir. Yes, sir. There will be
Okay,
need
okay. So
for,
we,
yes, sir.
We
so
definitely need your
wishing all the very
help
best from my
for
part.
guidance. Yes.
So wishing all the very best from my part. Okay.
Thank you, sir.
Thank you. Thank you. It's good. It's very nicely in the right direction. The works is going, I think.
Thank you, sir. Thank you.
Consider the age of the leaf. Suppose is a understood by
Yes, sir. Yes, sir.
age means whether they 5 weeks from the uh, age of the leaf is 5 weeks or 8 weeks, 14 weeks, something like that. That a leaf quality will be different.
Yes.
So, what is your range in your leaf sample?
Yes. Actually, sir, for actually when
Is it sensible?
yes, definitely, sir. So actually, we have already studied those things and consulted with the agricultural scientists regarding that. Actually, the main if we suppose if we try to take a image of already matured leaf, so this is where testing with a wrong data with but in cases where it is not matured, they have all majority rice has the same color. There is a green color in the leaf. Only 1 or 2% varieties are there, which are different colors like yellow or you can say purple color is there also. So, but for other rice cases or rice plants, so all the varieties has the same color. Maybe the variation is different, but we'll classify with the specific because the NPK we have taken because for a nitrogen deficient or potassium deficient or your phosphorus deficient like rice leaf images, they show specific symptoms. So which are not similar to other like other normal leaves. Yes.
When started this symptom, specific symptom, after you have to, I'm not able to express actually. Just suppose if I take 4 weeks, after 4 weeks,
4 weeks from transplantation, yeah.
and the 4 weeks, the page, leaf image
Yes.
of 1200 sample or 12,000 sample.
Yeah.
So from there, you will be predicting something. Again, if you say that 8 weeks to 12 weeks age.
Okay. Okay. Actually, if there is a deficiency in the soil, like NPK deficiency is there, so they will show the symptoms in any stages. Like in I can say seedling stage also, they can show in the vegetable stage also, or even in the flowering stage, they can show the same type of symptoms. So yes, sir, you giving a good suggestion that we can collect the images of this deficiency symptoms in different stages. So we are also planning to yes sir, we are planning, so we are planning the experiment in house. Actually we are to perform the whole experiment in house. Actually we put it in tub and we have the access to the experiment samples at any time, so we will collect in different uh, times, not specific to like 4 to 7 weeks. Not we'll collect some samples in 4 to 7 weeks, like or 4 to 8 weeks, 2 months, again on 3 months. We'll take because we need more number of samples with the more number of image samples with the lesser number of rice plants. So therefore we'll take samples in different stages. So maybe 4 to 5 stages will uh, take
There
the
also
time.
you can find out
Yes,
the
sir.
what stage is.
Yeah.
In that case, our
The nitrogen or phosphorus or
Dr. Bhavesh sir can give the best suggestion on that.
Uh, Bhavesh sir, please.
Oh, disconnect. So in that case, we have one scientist, agricultural scientist associated with us. So we can take suggestion from him. What is the peak period that we can collect the images, because if we go through all the different levels, then that again creates a complexity. Better than that, we can take the suggestion from the scientists that what is the peak period, so that from the sample, and then from those images we can directly go for implementing. Dr. Bhavesh sir can
Do the research on which would be the peak period to identify disease.
Sir, actually, we are currently we have already sown the seeds in the field, so which is nutrient sufficient. They are in the nutrient sufficient condition. So when we will transplant it to our tubs, then we will actually control their supplements, control the nutrients. So while when we control the nutrients, it will start showing the symptoms immediately. Like within 10 to 15 days, we will get symptoms. So that time we have to take the pictures actually.
And now next question is, are you doing this in the normal paddy field, or you are generating the
Sir, no, no, sir. We are actually
we actually planned for this, but এতিয়া আমাৰ হেৰিৰ কাৰণে আমি but the situation is climate is safe. Climate is safe because yes, in a paddy field that is the most favorable condition, but
control will not be there.
control will not
We cannot control the nutrient because due to the
yes, because maybe some nutrients are already there. Okay, so we cannot get the correct image out of that. No problem. So, I think you have correctly defended that last question. Okay, we can go to the next one. Dr. Puspendra sir, is everything okay from this presentation?
It's okay from my side.
Okay. So, any questions or any suggestion from the other members here? Otherwise, then, as we have already exceeded the time, we will come to the conclusion. And 2-3 suggestions already noted down that about the peak period time, what we have to consider, that we will take a note from our Dr. Bhavesh sir. And now, I would like to thank all the respected members, especially Dr. Puspendra sir, for with us from the last 2 hours, okay, and from the last 3 seminars, right? Thank you very much, sir. And all the other members. Dr. Puspendra, we will need your guidance for the coming seminars also.
Sure, sir.
Yeah, thank you very much.
Sorry.
No problem. So with this, we are concluding this seminar. And once again, thanks to all the members, all the students, and Dr. Bonida ma'am, and our respected HOD sir. Thank you.
Thank you. Good research is a fundamental one. Yes.